and welcome to our next module on linear block codes. Let's start with a brief outline for today's talk. Today we will look at linear block codes and then we will define what are equivalent codes. We will pose ourselves the question about efficient generation of linear block codes, and then we will look at the notion of a generator matrix. Finally, we will enter the decoding side of things and look at parity check matrix. So, this is the general outline for today's talk. As always, we will start with a brief recap of what we have already done. We have looked at block codes, we have defined Hamming distance and Hamming weights, then we looked at linear algebra, Galois fields, linear block codes, and we introduced this notion of a generator matrix. So, very quickly, what is a field or a Galois field? Well, a field is a set of elements with two operations, addition and multiplication defined, and it satisfies the following properties. It's closed under addition and multiplication. For A, B and C contained in the field F, we have the commutative law, the associative law and the distributive law. We have seen these before. And then we say that two elements must definitely exist in F which have certain special properties. These two elements are 0 and 1. What are the properties of zeros and 1? Well, any element A plus the 0 element should give you A. Similarly, any element A into 1 should give you A. And then for any element A in the field, we have an additive inverse always, such that A plus the additive inverse should lead to the element 0. Similarly, we should have a multiplicative inverse. A into A inverse should be 1, except for the element 0. All other elements in the field must have a multiplicative inverse. These properties are true for finite as well as infinite elements in the field. So, any set of elements, say Q elements, which satisfy all of these above mentioned properties are called Galois field. So, and it is denoted by GFQ. We have seen this before, and in the case when the last property, the absence of a multiplicative inverse is there, that is, we do not have a multiplicative inverse for each and every element, but all other properties are satisfied, we call it a ring. So, we now know what is a field and what is a ring. We will use this very commonly in our study of linear block codes. This is because we have put ourselves the condition that the sum of two code words must be a valid code word. And we have observed before that Galois in a very short period of time made major contributions in mathematics. We now quickly revisit the concept of a generator matrix. For that, we decide and make this following observation: any code C is a subspace of GFQN. Let's understand this statement with a simple example. So, if we take a very simple example, a code which is a lookup table, say 0 0 0 1 1 0 and 1 1, has please recall that K equal to 2 and N equal to 4 here. So, this is a 4, 2 code. These are my code words. But please see that even though only 4 information words are possible, 0 0, 0 1, 1 0 and 1 1 simply because my k is equal to 2. There are 2 raised to power 4, 16 possible words. But what we have done is we have only chosen a subset. A subset which is 0 0 0 0, 0 1 0 1, 1 0 1 0 and 1 1 1 1. Now clearly I could have picked up any other 4 words and put it in the table, and that would be yet another code. Right. A code is a set of code words. So this is my code. So if you go back to the statement, any code C is a subspace of GFQN, and in our binary case it is GF 2 raised to power n, and n is 4. So we have a subspace. Okay? So code is a subspace of GFQN. So we go back to our slides and make the observation that any set of basis vectors can be used to generate the code space. Now this is the critical observation. A set of basis vectors can be used to generate this space. We can therefore define a generator matrix G, the rows of which form the basis vectors for the subspace. Right? Now clearly, if they are to form the basis vectors, the rows of G would be linearly independent. This means a linear combination of the rows can be used to generate the code words of C because they form the basis vectors. Any linear combinations of these basis vectors would generate all other points in their subspace. Now this generator matrix will be of size k cross n, and it should have a rank k because there are k linearly independent rows, and n is necessarily larger than k. Now since the choice of the basis vectors is not unique, the generator matrix is obviously not unique for a given linear code, and therefore we will shortly see there could be equivalent codes. Why are they equivalent? In what respect are they equivalent? They are equivalent in terms of error correcting capability. We are yet to define that, but remember our aim is to have generator matrices for error correcting codes. Our aim is to correct from errors, recover from errors, and so in terms of the error correcting codes we will be able to have equivalent matrices, as we will shortly see. With this background and motivation, we would like to formally define. The generator matrix converts or encodes a vector of length k to a vector of length n. Clearly it is a k cross n. Let the input vector of uncoded symbols be represented by I. So I is 1 cross k, and the coded symbol then be represented by C equal to I times G. So C is 1 cross n is equal to 1 cross k into this dimension is k cross n. So you end up with a 1 cross n. Here C is called the code word, I is called the information word, and G is clearly the generator matrix. So now why is this generator matrix important? We saw last time generator matrix is indeed an efficient way to represent the lookup table. We saw that even if it is a moderately large k, then the lookup table size for a linear block code would grow exponentially with k, and it would very soon become impractical to have such large lookup tables, not only from the storage perspective but also from search perspective. On the other hand, a generator matrix generates a code word on the fly. It doesn't have a storage, it doesn't save the entire list. It just takes in the input vector and then generates on the fly the code word. This is the beauty of the generator matrix. The n cross k matrix can generate q raised to k code words in general. We're talking about a non-binary general case here. So this elements of the code word could be 0, 1, 2, 3 up to q minus 1. So instead of having a large, actually a very large lookup table of q raised to k code words, one can simply have a generator matrix, which is much more shorter. A very quick example, this is a 2 cross 3 generator matrix. So clearly k is equal to 2 and n is equal to 3. It will take in a vector of length 2 and generate vectors of length 3. What we have seen already is that the rows of the generator matrix must be linearly independent, which you can check very easily, and they form the basis vectors, which means that I can take the first row, multiply by scalar, add it up to the second row, and it will give me a valid code word. These themselves are two possible code words. So if you look at this example, if I want to generate the first code word, I can just multiply 0 0 with this and you get 0 0 zeros. Similarly, I can get the second code word by multiplying 0 1, which is the information word, with this to get 0 1 0, and same with the third one. 1 0 multiplied with generator matrix gives you this one, and similarly 4. So I know there are 4 code words and these are highlighted here, and each code word is of a block length n is equal to 3. A very simple example but an instructive one. So what have I been able to do? I have been able to use these 6 bits to generate a table which is 3 into 4, 12 bits. So already it is a highly compressed, efficient way to represent this lookup table. It can generate the lookup table. Okay? Instead of saving this 12 bits, I have just 3 bits and I will give you exactly these code words. Right? So this is the generator matrix for a n comma k, which is 3 comma 2 code, and the dimension of the generator matrix is 3 cross 2. Now we come to the notion of equivalent codes, and we will see they are very important and practical. So two query codes are called equivalent if one can be obtained from the other by one or both operations listed below. What are these operations? Permutations of the components and permutations of the position of the code words. So please note, these definitions are general but can be applied to binary as well. Query will become binary codes. Suppose a code contains m code words. So we keep emphasizing code is a set containing m code words, and this is in the form of a matrix m cross n. Please remember, m is the total number of code words, n is length of each code word. So m cross n represents this lookup table. Now operation 1 corresponds to relabeling of the symbols appearing in the given column. This is operation 1, permutations of components. Alright. And operation 2 represents the rearrangement of the columns of the matrix. This is permutations of the position of the code words. So intuitively, this slide tells us intuitively the properties of a code will not change if you do these things. Properties, the error correcting properties. the ability to correct errors, distinguish between different code words, that will not change if I carry out these two, and hence this is called the equivalent codes. Let us understand this using a simple example. So let's talk about a ternary code of block length 3. What do we mean by a ternary code? A code whose components take from the elements 0, 1 and 2. Okay. So let's take a simple example. So my code, which is a set of code words, it has only 3 code words: 201, 120 and 1012. Now just a mere scrutiny of this lookup table tells me that this is indeed a 3,1 code. Why is it a 3,1? N is equal to 3 is obvious, because each of these vectors, each of these code words is of length 3. But why is it 1? K is equal to 1. K is equal to 1 means the information word length is 1, that is either a 0 comes in, or a 1 comes in, or a 2 comes in. So if I were to represent this code in terms of a lookup table, I would do the following. I have here k equal to 1 and I have got n equal to 3. So what we do is possible inputs are 0, 1 and 2. I am writing out this example now, and then 0 is represented by 2, 0, 1, 1 gets represented by 1, 2, 0 and 2 gets represented by 0, 1, 2. Now if you look at this example that I am writing out, you will see that this is not a linear code. It is a block code, but the all 0 code word is missing. And on the other hand, if you try to add any two code words, and here the arithmetic will be over GF3, okay. Sum of any two code words is not another valid code word. For example, if you add these two, 2 plus 1, 0, because it is a Galva 3 addition, so modular arithmetic will hold because 3 is a prime, 2 plus 0 is 2, 1 plus 0 is 1. So sum of these two code words is not a valid code word. So it defies both the properties of a linear block code. Nonetheless, it is a valid code. It's a block code. Now the question is, can we find an equivalent code for this? So we apply those permutations that we discussed in the previous slide. Let's say 0 becomes 2, because what is a 0? It's an element. What is a 2? It's another element, and nobody is bigger or smaller than anybody else. It is just a collection of symbols. So 0 becomes 2, 2 becomes 1, 1 becomes 0, and you have to apply these two transformations to columns 2 and 3, and suddenly you can come up with the following equivalent code. So let's observe these two before and after case. Before applying those permutations and after applying those permutations, we see that code C1, which is an equivalent code, is nothing but a repetition code. 0 becomes 0, 0, 0, 1 becomes 1, 1, 1 and 2 as an input becomes 2, 2, 2. It is nothing but a ternary repetition code. The other important observation is that the original code clearly is not linear. We just checked. But this equivalent code is linear. What does it mean? Well, all 0 code word is a valid code word. The sum of any two code words, 1 plus 2 0, 1 plus 2 0, 1 plus 2. So, sum of these two is this, and sum with 1 1 1 with 0 0 0 is self, and so on and so forth. So, you can check that any pair when added together yields another valid code word. So, C1, which is equivalent, is a linear block code, whereas the first one is not. So, let us go to a formal definition. Two linear query codes are called equivalent if one can be obtained from the other by one or both operations listed below. Multiplication of the components by a non-zero scalar, permutation of the position of the code words. Okay. So, this is what we had stated earlier, but now we are formally defining how we can declare two query codes to be equivalent. Please note, already we have seen value in declaring or making equivalent codes, because there are very nice techniques available to handle or generate linear block codes, but not so for general block codes. And if you can convert a general block code to a specifically to a linear block code, we can make our lives much simpler. Now, let us talk about equivalent linear codes. So, first we have looked at a non-linear code being made equivalent to a linear code. Now, I can have one linear code being made equivalent to another linear code. The moment we have a linear code, we have the luxury of the generator matrix. Okay, that is an important observation. If you have a linear code, you can represent it using a generator matrix. Now, we are talking about two linear codes and we want to show the equivalence. So, we have two k cross n matrices. These are generator matrices, code 1, code 2, and they are supposed to generate equivalent linear codes over GFQ if one of the generator matrix can be obtained from the other generator matrix by a sequence of the following operations. So, we are defining 5 operations, okay, and by conducting these 5 operations in any sequence and combination, if I can convert one of the generator matrix into another, then these two are termed as equivalent linear codes. So, this sequence could be anything, okay, and it could be just the permutation of rows. One permutation of rows can lead to the other generator matrix. Multiplication of a row by a non-scalar, addition of a scalar multiple of one row to the other. Take 2 rows, add them up, put it as a third row. Permutations of column, interchange column 3 and 5, you end up with an equivalent linear code. Multiplication by any column by a non-zero scalar. All these operations in any sequence, if leads from one matrix to the other, then those two matrices, generator matrices, are called equivalent linear codes. So, here we are talking about a vector versus a scalar. So, let us show this as an example. The question being asked is, what is a scalar here? So, if we look at this example of a simple generator matrix, in this case we have 2 rows. So, k equal to 2 and n equal to 4. In this case, it is a code over GF2. So, there are 2 elements in the set 0 and 1, and we have already ruled out multiplication by 0. So, multiplication by scalar is multiplying any of the rows by 1. So, it really does not change that. But if you want to make this example non-trivial, let us talk about GF3. and I have got another generator matrix which we saw in the last class. Well, in this case, this is not the matrix we are talking about, but this is the code that we talked about. So let's talk about this code. This code is a lookup table and can be written also as so here n is equal to 3 and k is equal to 1. Okay? Therefore, we have 3 elements in that lookup table. So if you have to have the generator matrix, the size should be k cross n 1 cross 3. So the generator matrix is nothing but 1 1 1. How does it work? Well, you multiply it with 0, it becomes 0 0 0. If you multiply it with 1, it becomes 1 1 1. If you multiply it by 2, it becomes 2 2 2. So you have this generator matrix generated. Coming back to the question, what is a scalar? Now since this is over GF3, we have the elements 0, 1 and 2. So I can multiply this G by a scalar 2. So I can get G1, if I multiply this row by 2, I have the multiplication table for GF3, so I get 2 2 2. Now clearly this is generator matrix 1 and this is the other generator matrix. These two are equivalent simply because I multiplied one of the rows with a scalar. A vector would be a vector could be like 1 2 1. This could be a vector. We don't entertain multiplication by a vector. It will change the dimension and other things. Just a scalar multiplication means you multiply with any one of the elements which is non-zero. So I multiply it with a 1 which leaves it unchanged, or I multiply it with 2. So the point to be noted is we have just created these two as linear codes which are equivalent by scalar multiplication of this row by 2. So the scalar is 2. Now we come back to our slides and we define another interesting method of representing the linear block codes. A generator matrix can be reduced to its systematic form, which is also called as the standard form, of the type G is partitioned into an identity matrix I and a matrix P which is called the parity matrix. So G, if you note, is k cross n and I is a k cross k identity matrix and P is a k cross n minus k matrix. So if you now go back to the drawing board and have a look, you have this G matrix which we now define in terms of an identity matrix first. So we have 1 0 0 So this is k and this is k. What we are left with is now n minus k on one side, and again this is k. So my P matrix is of the dimension k cross n minus k. this is called the systematic form. So, a generative matrix can be reduced to its systematic form of this type by those basic row and column operations. And the proof is pretty intuitive. The k rows of a generative matrix are linearly independent. We saw that they form the basis vectors. Hence, by performing elementary row operations and column permutations, remember there are k rows. So, you will be able to place a single 1 and all zeros in the first few columns and thereby obtain the row echelon form, and the matrix will be of the form I partition P. Okay. Because very simply you have got rank k matrix, there are k rows. So, first k rows of the matrix can easily be converted into linearly independent. So, all of them will have a single 1 which does not overlap with the following columns. So, let us look at an example. Let us consider the generative matrix for a 4,3 code over GF3. What does it mean? It means that the size of the generative matrix is K3 by 4, and GF3 represents that the elements of the generative matrix will be 0 or 1 or 2, and all the arithmetic, the addition and the multiplication would be carried over GF3, which will be modulo 3 arithmetic. So, the example is as follows. G is again a 3 cross 4 generative matrix, and it tells you that the k value is 3. Now, we can start doing our basic row and column operations, and this requires a little bit of thinking, observation, and see, because right now there is no single 1 in any column. What are we trying to do? You observe the first column 0 1 1. Well, what we need is a 0 0 1, a single 1 in 3 columns, and then interchange of columns is very easy. We have discussed that before. They will lead to equivalent codes. So, we are trying to make an equivalent code starting from this jumble of numbers. So, if you represent the ith row by Ri and jth column by Rj, what we can do is replace R3 last row by R3 minus R1 minus R2. So, I am doing this basic operations. So, R3, then R1 first one and R2, but please remember it is equivalent to saying R3 plus 2 times R1 plus 2 times R2, because minus 1 is equal to 2 in GF3. Why is that? Because 1 plus 2 is 0. So, 2 is equal to minus 1 or minus 2 is equal to 1. So, either I do this statement R3 minus R1 minus R2, or I can say that R3 plus 2R1 plus 2R2. So, I can 2R1 is multiplying the row 1 by a scalar 2, and then again taking the row 2, multiplying it with another scalar which is 2 and adding them up. So, addition of rows are permitted, you still end up with an equivalent code. We do that, and if you do that basic operation, you get the first 2 rows untouched because I have only replaced R3. And if you do so, first 2 rows are the same, R3 is changed by doing this operations, you can check that, and still we are far from done. How did it help us? Well, look at the first column. First column helped me get rid of this 1. So, in this first column there is only a single 1 and rest are all zeros. So, parts of the juggle, the jigsaw puzzle are fitting together. this will form my second column of my identity matrix. Look at this last column 1 0 0. The previous operation led me to a single 1 in this column. So this will hopefully form the first column of my identity matrix. But those are the two ones. I still need to get a 0 0 1 somewhere. I need to knock off this 1 somewhere by carefully thinking how to scalar multiply this and that. So my first gut feeling to knock this off is 1 plus 2 is 0. So I have to add a 2 here. Now I observe in the last row that there is a 1 here. So if I multiply by a scalar 2 here, so this will become 0, 2, and 2 into 2 is modulo 3 operation is 1 and 0. So the moment I have a 2 and I add this to the first row, I will be able to get a 0 here. This will remain unchanged and this will remain unchanged. So that will be a logical step to go. But we can do some other things. So we can replace R1 by R1 minus R3 and we can get another kind of a thing. So we have got 0 1 0, 0 0 1, 1 0 0 as 3 columns which are candidates for my identity matrix in the beginning. All I have to do is interchange the columns. The order of the columns can be changed. So I do that, C4 goes to C1, C1, these are columns, column 1 becomes column 2, column 2 becomes so and so forth, and then suddenly things fall into place. Alright. So I can take this thing and do the interchanging and I can see suddenly that very clearly this is a identity matrix in the beginning, and whatever else remains, this 0 1 2 which remains is the P, the parity matrix. So these steps just tells us how we can use the basic row and column operations to convert a generator matrix into the systematic form, which is the standard form. Now so far we have only talked about efficient representation and encoding process. We have not talked about decoding. But one of the stated objectives of a good error control code is an efficient encoding as well as a decoding process. So let's focus our attention on efficient decoding. We have dealt with efficient generation. Can we have an equivalent decoding matrix? Okay, because we can't say that look, we have reduced the problem of lookup table at the transmission side, but at the receiving end why don't you have your lookup table? You've received a valid code word, look it up and reverse and try to get back the original information word. So is it possible to detect a code word is valid quickly? One of the ways which is inefficient is to go through the long table, the lookup table, and check whether it matches, but that is a pain. So question is, can we have a very nice matrix representation to do the same thing? The answer of course is yes. It's the question we have posed. The answer lies in the parity check matrix, typically denoted by H. But what properties should this parity check matrix have? Now word of caution, this is called the parity check matrix. What we have seen earlier was the parity matrix P when we formed the systematic representation of a generator matrix. So please note the difference. We have seen the parity matrix for the systematic form and now we are talking about the parity check matrix H at the decoding side. Now what is our wish list? This parity check matrix, as the name suggests, should be able to see whether the code word is valid or not. So my wish list is that any valid code word C when multiplied with H transform should give me a 0 vector. On the other hand, if C is not a valid code word, then I should get a non-zero vector here. Okay. So if I can have this going for me, then I indeed hit jackpot, and I should be able to very quickly detect. First step is detection, detect if there is an error or not. Now we make a quick observation. What is C? C after all is I into G. I is the information word, G is the generator matrix. So if you put that C equal to Ig in this first equation, we get I G T G H transpose equal to 0 for all possible information word. I cannot have it specific to any particular information word. This means that I should have GH transpose equal to 0 in order to make it general enough for all information word. So if we have a generator matrix, we should be able to find out an H matrix, and also vice versa. If I have an H matrix, I should be able to find a generator matrix. Now how do we do that? Well, one of the bigger, longer, strenuous way is to represent this H matrix generally by the elements H11, H12, H13 for different rows, and you already have a G matrix, then you have a set of linear equations and you solve it. You will realize that this problem is under constraint and you can have several solutions for H. So it tells us that the H matrix need not be unique. You can have several valid parity check matrices for one particular G matrix. You can check it out. Okay. Now the size of the parity check matrix is n minus k cross n. This parity check matrix provides a very simple and elegant way of detecting whether an error has occurred or not. If the multiplication of the received word at the receiver with the transpose of H yields a non-zero vectors, it raises the flag. It implies that the error has occurred. Now question is, what error? And if we can answer that, what error, then we would be able to go back and correct the error. Okay. However, this methodology will fail if the number of errors in the code word exceeds the number of errors for which the coding scheme is designed. So this brings us to a very interesting observation. Error control codes are designed for a certain number of errors. So if the number of errors are within the limit, everything works well. But if you exceed, then all of these decoding mechanisms will start failing. So let's just look at a smart way to generate a parity check matrix. We've already seen that G matrix can be represented as in the standard systematic form, identity matrix and a parity matrix. Right. P is sometimes also called as the coefficient matrix, but in general we will call it as the parity matrix. So now the parity check matrix can simply be defined as minus P transpose and I, but this I will be n cross n minus k. So PT represents the transpose of the matrix P, and this is easy to verify. If you have your GH transpose and G is in the systematic form I in I partition P, and you have this minus P transpose, here there is a transpose I, and if you multiply it out you will end up getting a 0 matrix. Let us go for a quick example. Let us talk about the 7,4 linear block code. So the generator matrix for this is given as follows. You can check that there are 4 rows and 7 columns, thereby making it as a 7,4 linear block code. It is for our convenience set in the systematic form, so you can clearly identify an identity matrix K equal to 4 here, and here is a parity matrix. So I can draw that line and you can easily visualize IP. Now if you were to find out the corresponding, so parity matrix, first we highlight this because ultimately our aim is to find out the parity check matrix. But P matrix is this part, so we write this P matrix out explicitly because we have to take minus P transpose. If you remember that in order to calculate H, we need minus P transpose and then just replace with I. So let's go with this P, and the first stop is to find out what is P, which is very clearly given here. Now to get the P transpose, just tip it over and we have now a 3 cross 4 P transpose matrix. Now we have to put a negative sign, but we are working with binary codes. Binary means 1 plus 1 is 0, so minus 1 is 1, minus is plus, so minus P transpose is nothing but P transpose. So we have already got that stuff. All we have to do is append the I n minus k matrix here. Now n is 7, k is 4, so n minus k is 3. So we must append a 3 cross 3 identity matrix at the back and we are home free. So H is minus P transpose partition I, this we have already figured out, and we put this 3 cross 3 matrix at the back and we have our H matrix. So this H matrix should be able to give you a 0 vector output for any valid code word generated by this generator matrix. So with this we come to the end of this lecture. Just let's summarize what we have learned so far. We started looking at linear block codes, then we spent some time looking at equivalent codes because they are pretty helpful. They are very handy mathematical tools to how to make one code equivalent to another code. Then we looked at the notion of generator matrices, and finally we moved over to the decoding side and looked at parity check matrix. Of course, we looked at a few examples on the way. With that, we come to the end of this lecture.